Hello, everyone. Welcome to today's webinar. Today we're talking Safe Schema Updates, Part 1, Imagining Better Systems. So let's jump into some housekeeping. You won't need to record today's session. What we'll be doing is we'll be emailing you generally within 24 hours of all the sessions ending with a YouTube link. We will have around 10 minutes at the end of today's webinar where we're going to be taking your Q&A. Please do use Zoom Q&A. Where possible, try and not use Zoom messaging. We don't always capture the questions using Zoom messaging. You can also, if you are streaming it on YouTube as well, please do use the comment feature within Octopus on YouTube so that we can, and we'll answer your questions there. You can also join our community Slack on octopus.com/Slack. If you put your question into the webinar channel, we'll get that question. And I'll be presenting those to Alex Yates. So at this point, I'm going to introduce you to the speaker today. Hey, Alex, how are you?
I'm good. How are you, Derek?
I'm good. I'm really excited about today's talk webinar. I think it's going to be a really great one.
Thank you. It's one of my favorite topics.
Yeah, it's really good. And obviously we've ran through it a few times. So for those on today's webinar, you're in for a treat. At this point, I'm going to hand you over to Alex, and he can get started.
Cool. Thank you very much, Derek. So this talk originated as a blog post, which then turned into a whole series of blog posts. The first one I started writing was this one down here, part 7. And I wanted to write about zero downtime database deployments because I felt that they were underappreciated as a way of keeping our systems safe. And so then I got on to talking about how we keep our systems safe. And before I knew it, I'd written an 8-part series. So this webinar is kind of the first chunk of it, the bit where I'm going to look at the way that we build our systems at the moment and everything that's wrong with that. And then I'm going to talk about things that we can do that invert various vicious circles and things that help us to avoid building bad systems and to build good systems instead. That's as far as we're going to get today. We're going to imagine what a better world will look like. And next time, we'll talk about how we can deliver that better world. So let's get started. And the first thing we need to do is talk about the dreadful state that so many of us find ourselves in. And for this, I'm taking inspiration from Gianluca Sartori, one of my friends in the SQL Server community, who delivered an excellent talk at GroupBy a few years ago called Database Infernals. Google Database Infernals, groupby.com.org. It's an excellent talk. I highly recommend it. Anyway, I've taken his idea, completely shamelessly stolen it, and I'm applying it to database DevOps instead. The first level of Dante's database hell is the data itself. Managing database updates is really difficult because of the data. Now, before I get too deep into this, my history is mostly with relational databases and specifically SQL Server, so that's mainly what I'm drawing on for this talk. However, I suspect that most of the stuff I'm going to talk about today is generally applicable whatever your data, but basically whatever persistent storage you have under the hood. Obviously, foreign keys don't help with respect to dependencies and things, and that'll become obvious when we get there, but generally a lot of the problems here are specifically related to any sort of persistent storage. And the reason for that is it's very difficult to treat persistent storage like cattle rather than pets, as the old DevOps saying goes. I can't just drop and create my databases because there's data in them and I'm going to lose it. What that means is every single deployment I'm deploying in situ. I'm moving bits and bytes around. That obviously introduces some element of risk. Poor performance can wipe you out. If you've forgotten an index and you've started a database update that you can't back out of, then you're sat there twiddling your thumbs until it's done. This sort of stuff can be hard to test in advance because development and test environments typically aren't spec'd out the same way that production environments are. They typically don't have as much data. They may well not have representative data. The distributions might not be as right, which makes it hard sometimes to predict how queries are going to run by the time you get to production. This is often one of the reasons why you see the experienced database administrators or whatever who understand how stuff runs in production getting frustrated with the people that just don't have access to that level of information or that level of experience. And that causes a whole bunch of problems. So it's hard to test this stuff in advance. Our development environments rarely look like production. Problems, when they do occur, can be disastrous. They can cause a huge amount of slow running. We can lose data, and rollbacks are either hard or impossible depending on how you define the state that you want to roll back to, for various different reasons that we'll get into. So the data itself, already off the bat, we already have a whole bunch of challenges. These are exacerbated by dependencies. Databases are heavily normalized databases act like gravity. Foreign keys suck up dependencies like a black hole. And these databases become a single source of failure to so many systems because so many different applications and services are dependent on this one big monolithic database that just sits in the middle, gathering weight and momentum and just sucking everything into it. That means that we have a single point of failure, which leads to global failures. When the database goes down, everything goes down. So not only are my deployments scary and risky and hard and performance intensive, but when they go wrong, everything goes wrong. People get scared when they talk about making changes to the database, which is why the topic of safe schema updates I think is so important. We also have to deal with this release coordination hell. Because of this because of this dependency hell, we end up with release coordination. What I mean by this is, in order to release my update, it's not just an update to one thing, it's an update to several things, the database, this application, that service. So you need to release all of the respective things, probably in the correct order, one at a time. So you've got a whole bunch of very specialized people sat in a row, or at each other's desks, whatever, ready to hit F5. And if any one link in the chain goes wrong, then we need to unpick everything before the end of our downtime window. Downtime windows are a whole problem, especially in tangled up big ball of mud systems, because nobody wants a downtime window. My users don't want it. Other parts of the business don't want it. When the database affects everything, that means everyone wants to stop you putting in a downtime window. Which means that in order to get your downtime window to perform this update, you need to negotiate with 150 people around the business. When you eventually get it, it's never for as long as you want, and it's always further in the future. And you've got stuff you need to get done, which means that you're going to pack as much stuff into it because these downtime windows don't come around very often, which exacerbates everything above. One of the disasters they had in the Phoenix project was a classic example of all of this mixed together. They had a downtime window. They had to be back online by first thing Monday morning, otherwise catastrophe. They released a database update. They were missing an index. The thing was running much, much more slowly than they'd anticipated, and they couldn't back out of it. They just had to let it run, which meant that none of the systems could be brought back online on Monday morning, and they completely hammered operations, sales, marketing, like everything, accounting, everything was broken in the morning. They couldn't pay their staff. It was headline news. Like, it was the absolute perfect storm problem, and it was a result of all of these things, which actually are common to so many of us. As a result of the risk, we end up with bureaucracy hell. So this is where, because of the risk of this all going wrong, we need to wrap up these downtime windows and all sorts of patterns and practices to reduce risk. And by reduce risk, what we're saying is we need to make sure that we've avoided any chance that this is going to go wrong. It has to go right. But what this does is it introduces a whole bunch more politics and delays and slowness into the system, which means it's even longer before we get our downtime window, and we have to pack even more into it, which means it's even more likely that we're going to have a problem. This is why change approval boards and things don't work the vast majority of the time. The data backs it up. Go read Accelerate. Go read anything I've written about change approval boards on the Octopus blog before. What this also leads to is this counterculture of a disobedience of bureaucracy, clever form filling, massaging the truth to avoid going through this change approval process, shadow IT, because using the officially sanctioned systems is so slow and bureaucratic. It's harder than just spinning up your own thing and managing it yourself. So that's what people want to do, and then you end up with all the problems that shadow IT brings. You get all sorts of politicking to avoid going through the processes that we try to put in place to fix these problems. The theatre of security becomes more important than security itself, and this leads to negligence. Now, to explain this, I'm going to bring up, again, I'm going to use the Phoenix project, the 4 types of work. So Gene Kim talks about 4 types of work. The first one is business projects. That's actually the stuff that you want to do. This is what most people think we do spend all of our time on, building whatever it is, our product. The next thing is internal projects. This is all the stuff we do to help us with business projects. The internal improvement stuff, setting up monitoring systems, setting up deployment pipelines, all of the stuff that we do to improve our internal processes to help us to be better at delivering the business projects. The next thing is changes or updates. This is that administrative toil, updating servers, executing deployments, all of just the admin of moving bits and pieces about, the just general service administration type stuff. And then finally, we've got unplanned work, firefighting. Now, you're probably looking at this image right now. There's a lot of firefighting going on because there are a lot of fires. As you've seen, as we've worked our way down the levels of hell, stuff's going wrong all over the place. We've not accounted for that in our weekly planning, which means we've got to find some time from somewhere, which means something else has got to give. And eventually, because of the amount of technical debt we're building up, and for those that don't know technical debt is where you take a shortcut and to achieve something quickly. And the impact of that is you've created yourself some work that you need to do in the future. There's an extra administration cost or something. You've taken a shortcut to get somewhere, but you know you're paying a cost for it down the line. That cost is called technical debt. You're kind of borrowing time from the future so that you can get something out the door right now. And as any economist will tell you, a healthy level of borrowing is good. It gives you a competitive advantage. But too much borrowing will cripple you because the interest payments get too much. Well, with too much negligence, because of all the unplanned work that's come along, you've underinvested in your internal projects because you've not had time to focus on getting better. You're just trying to tread water and keep up with the pace. You start cutting corners to do that. The amount of technical debt builds up and you reach the technical debt singularity. This is where 100% of the hours that are available to you are spent firefighting. You might be able to hack around it for a little bit by asking people to do overtime. You might be able to hire more people, but as we learned in the 1970s with the Mythical Man Month, hiring more people isn't likely to solve these problems. Ultimately, either you need to change the way that you approach risk and manage all of this, or one of your competitors will. And if you're in a competitive industry, that's often curtains. So, this is bad. This is what we want to avoid, but most of us, if we work with large databases of some sort or other, probably recognize ourselves as somewhere down this scale, and it feels like each month, each year, we're descending deeper into the pits of hell. Without making changes to the way that we approach things, we're not going to change that trajectory. So, how do we change our trajectory to help us escape hell, reach something that might be described as heaven? Well, over the course of this webinar, I'm going to talk through 4 areas which I think really, really help. The first is resilience versus robustness. I'll get on to talking a bit about more. I'll describe that in a bit more detail shortly. I'm then going to talk about continuous integration. And specifically, I'm going to talk about it in its true sense rather than the cheap understanding that I feel a lot of people have. A lot of people, I think, misunderstand continuous integration. And I think that it's only continuous integration in its true form that actually helps significantly. I'm then going to talk about loose coupling, which arguably is just one more thing, but I'm going to actually split loose coupling into two separate subpoints. First of all, I'm going to talk about it from a technical perspective, and then I'm going to talk about it from a human perspective. So arguably loose coupling is just one thing, maybe it's two things, but while the human and technical parts of your system are inextricably linked, and loose coupling is a broad tool that's going to help us solve all the various different bits of that problem at a systems level. Specifically, the way that we solve problems associated with servers and the way that we solve problems associated with humans are very, very different. I don't want to treat my people like cattle. So I'm going to split those up into two separate groups, and I'm going to try and address each as they deserve to be treated. And that's the agenda for today. So that's what we're going to talk about. I'm not going to talk in too much detail about how we deliver a loosely coupled system. I'm going to talk about the benefits of it today and how it's better than a tightly coupled system with a big monolithic database at the center of it all. I'm going to talk about that today. Next time, we'll talk about how we migrate from one state of affairs to another, how we gradually re-engineer our system, how we refactor it into a different state of affairs. That's a very difficult challenge. There are all sorts of aspects to it, and that will be a whole webinar next week that will next fortnight that will cover that. So resilience and robustness. How do we define resilience and robustness? Well, to define resilience and robustness, first I want to talk a little bit about the difference between complexity and complicated. Complex versus complicated systems. A lot of us use these words interchangeably, but they do mean subtly but specifically different things. A complicated system is something that's hard to understand, but crucially it can be understood like a complicated maths equation. So encryption algorithms, for example, they are predictable. You can hard crank them if you want to. It just requires a calculator and more lifetimes than you have available to you to go through the sums one by one by one. Eventually you'll get them. If I was smart enough to understand them, if I had a book available to me, if I had a chart with all of the prime numbers up to like the highest prime numbers that we know today, and I could easily navigate all those numbers in a sane way, I could hard crank it. Of course, I'm not going to, because I'm not nearly that smart. I don't understand the algorithms in detail, and I don't have many hundreds of lifetimes available to me to go through and do the sums. It's impractical, but in theory, it's possible. These things are understandable and crackable. Complex things are things that have an element of unpredictability in them, such as the weather. Our best prediction of the weather is only a best prediction. It's not certain. Our sensors don't give us a complete picture of what's happening with the weather. Our supercomputers are algorithms that are a pretty good approximation of the best state of affairs of current knowledge with respect to meteorology. But like, it's an ongoing science. Like, we're still learning about how the weather works and how climate works. So while we've got a really good idea about it, and like, it's certainly not a myth, like this is definitely happening, we don't understand it all 100% yet. There's still a level of unpredictability there because we just don't have all the answers. We don't have all the data in perfect detail, which means the best we can do is say it's probably going to do this, and most of the time we'll be right. Now, in any software system that relies on humans to support, maintain, fix, in any system like that, and the humans are part of the system, it is fundamentally complex because humans are complex, and humans are complex because humans are unpredictable, and humans are unpredictable because we haven't yet mapped out free will. And already I feel like I'm going down a rabbit hole that I'm uncomfortable going any further down because somebody's going to hit me in the comments. Like, I cannot predict exactly how another human being is going to act in any given scenario. I can make a reasonable guess, and a lot of the time I might be right, but it's never going to be 100%. Which means that any system that relies on humans is fundamentally complex, which means that pretty much any enterprise software system is probably complex rather than complicated. So, we've established that complex systems have a level of unpredictability about them in many ways due to the humans, but also due to any undocumented or poorly understood dependencies or something within your code. So, for example, if you've got any parts of your system for which you've lost the source code and there's no documentation, which I've seen before, you could argue that there's a certain amount of unpredictability there because you don't know how it's going to respond, and you're not able to, you're not practically able to unpick that easily. So it would be really great if we knew a bit about failure in complex systems. And there is a fantastic piece of academic work that was completed by Richard Cook in the I'm going to say the early 2000s or the 1990s. I can't remember exactly when it was. I apologize for that. Somebody will hit me with that in the comments or the Q&A or something. But this got tweeted out by John Allspore from the 10 Deploys a Day talk, and kind of everybody from that point, it just went viral around the DevOps community. Back in the day when we kind of defined DevOps as lean manufacturing, suddenly this came up and it was like, hang on, this speaks to me. Even though he's talking about hospitals, in IT we instinctively knew that it was true for us too. And by the way, when I'm talking about hazardous systems, you think as an IT person you work with a hazardous system. I bet you've never worked at an operating theatre before. Like, people don't, depending on the software that you're working on, people don't often die when we screw up a deployment. So that puts the nature of failure, like the definition of catastrophe is very different in a hospital for what most of it, for the way most of it experience it in IT. Anyway, after doing a bunch of research, Richard Cook came to 18 conclusions. And I highly recommend that you read this in full. It's an easy to remember URL, how.complexsystems.fail. I'm not going to call out every single one of these 18 points because we'll be here all day and I don't have enough time for that. But there are a few things that I want to highlight specifically. First of all, complex systems are intrinsically hazardous systems, and they're heavily successfully defended against failure. We already have all sorts of mitigating factors in our system that defend us from failure all the time. And crucially, single points of failure happen regularly. Sorry. Single points of failure are not enough. Individual things fail often, but because of the mitigating factors we've put in place, any one thing by itself probably will recover from. It's when multiple things go wrong at the same time in unpredictable ways that suddenly we end up with weird failures because this thing has failed and that thing has failed and that thing has failed at the same time. And if you look at most of the big failures in history, it's a whole bunch of things happened that went wrong. And I could go through examples, but we'll be here all day. As a result of this, I'm going to skip through a little bit. Post-accident attribution of root cause is fundamentally wrong, and the view of root cause, it's down here somewhere, views of cause limit the effectiveness of defenses against future events. So because our failures typically rely on multiple things going wrong in multiple places, the idea that any one of them is individually at fault for everything is just wrong. And as a result, but if we take that mindset, it's only going to have a limited effectiveness because we were incorrect about why the thing failed to begin with. So any measures that we put in place to try and protect ourselves from failure aren't going to work anyway. We have to accept that anything and everything at some point, given enough time, will go wrong. So we need to build our systems to carry on running when these individual points do fail. And we need to be more concerned about the how the various different failures are interacting with each other rather than being concerned about any one individual thing, which is really hard. It like takes a mental leap to be able to get to that level. I'm not saying that barely anybody is there yet, but these are the ways that we need to be thinking about it. The other really critical thing that I want to talk about is the role of humans within complex systems. It's in here somewhere. Human practitioners are the adaptable element of complex systems. Like, the humans are not the risk vector here. Or they are a risk vector, but they are also your salvation. It is the humans, like the system itself. The system isn't going to fix itself. It's not going to improve itself. It takes humans to engineer that. It takes humans to, right at the moment it still does. We'll see where AI goes. But it takes humans to build safer, more reliable systems. It takes humans to maintain them. And failure-free operations requires experience with failure. So if your humans are never getting the opportunity to work with failure, to experience failure, they're going to be rubbish at dealing with it. It's one of the big paradoxes of the whole thing. People continuously create safety, and it's only through experience with failure that they're able to build that safety. So the objective is not to avoid failure. The objective is to avoid catastrophes. Failures happen all the time, but we need to experience those failures. We need to deal with those failures. We need to be running those failures and practicing those failures and detecting those failures and automating the resolution of those failures. That would be what a mature approach to risk looks like. So this safety 2.0 safety culture movement, which was massively picked up by healthcare, by aerospace, by various other industries, was embraced by the DevOps community as well, just like it had previously adopted lean manufacturing. And it spurred on the resilience engineering movement, if you like, within DevOps. And trying to define resilience engineering, it's one of those things that I'm not going to try and define it myself. What I really like, and I referenced it in the blog post about resilience here, is a blog post by in one of my favorite books, Database Reliability Engineering by Lane Campbell and Charity Majors. I've got the whole quote here. Read the blog post, read the book. I'm going to focus on the three aspects that Campbell and Majors say are like the key attributes of resilience engineering. The first one is mean time to recovery over mean time between failures. So what I'm saying here is, you know those signs that say it's been however many days since our last accident? Well, none of that, please. We recognize that failures happen all the time. Of course, if somebody's actually been hurt or injured, then that's a bit different. But in IT, if we're talking about an amount of time that our service wasn't available, typically we're not talking about deaths or serious injuries. So rather than focusing on avoiding failures happening, we're focusing on how quickly can we recover from them. In a world where us being down is typically, we're talking about downtime, how long is it before I've brought the systems back online and restored all the data? How long does that take? If I can do that in 5 seconds, for most systems, does it really matter so much if I have an outage? There will be the odd system where it does matter, but for most systems, is 5 seconds good enough for you? Most people would probably say yes. Also, how impactful is it for those 5 seconds? What if, rather than affecting all of your customers, it only affected a handful? If I've only affected a handful of people for a fraction of a few seconds, is it really a catastrophe? Probably not. And ultimately, we're talking about the ability to treat these failures as a normal part of the system. Not only are they so normal that I can handle them so well, they're so normal that I'm injecting them into my system. And this is where chaos engineering comes in, which is so fun. I'm injecting them into my system so that I can constantly practice them and rehearse them and refine my automated steps to mitigate them and my human steps, like game days and things, where we get all the engineers in a room and say, right, we're going to fake out in production our perfect storm of everything that could go wrong. All of our AWS data centers that we're using go down. We're going to fake that out. Right, deal with it. How quickly can you fix it? In production. Probably in these scenarios, you've got some sort of kill switch where you can bring everything back online quickly, just in case everything goes too pear-shaped. But the point is, if we can work like this, embracing failure and dealing with failure and practicing failure, that means that we're far better equipped to deal with stuff when it actually does go wrong. We're far less likely to go down. This is how Netflix famously stay online, for example, when there are AWS outages, which is where they do the hosting, when all of the other systems that are based on AWS tend to fail, because Netflix are excellent at this. Go read about Chaos Monkey. I talk about it further in this blog post if you're interested. So that's resilience engineering. We focus on mean time to restore over mean time between failure. We focus on minimizing impact, and we focus on treating failure as a normal part of the process. So that's the first thing that we need to do. The next thing that we need to do is embrace continuous integration in its true form. Now, if I ask you what is continuous integration, can you define it for me? A lot of you, and I'm not saying all of you, but a lot of you will probably respond with something along the lines of some sort of automated build or test every time I commit to source control to tell me that everything is right. And I say, well, why do you run those automated builds? And you might say to catch problems early, to catch mistakes, to make sure that I'm building quality into my product, that I'm always writing clean code. The earlier I catch my mistake, the cheaper it is to fix, the easier it is to fix. And so that's what I'm trying to do. And my response would be, yeah, that's all great. But that isn't continuous integration. Automated testing, automated builds are not the end, they are the means. It is through automated builds, continuous tests, it is through that we enable the rapid, frequent integration of our changes. The whole point is to avoid big merges, big deployments. We're trying to avoid a big delta between the dev environment and the production environment. We're trying to avoid a big delta between this branch and that branch. We're trying to keep everything fairly close to one thing so that my code is basically just what's on mainline. That's all I care about. And anything that's different from that is only a small piece of work that can easily be merged in when it's ready. To that end, this is the first image that the wonderful designers at Octopus provided for me when I first provided the continuous integration blog post. And I said, thank you, but I'm not happy with this. And the reason I'm not happy with it is just like every single other diagram you tend to see on continuous, just like most other diagrams you see to represent continuous integration, there's a cycle, because there's always a cycle, because we love a good cycle. But the merge, you'll see, is just one little circle on kind of 3/4 of the way around this cycle. It's got it wrong. It's put the continuous part as the thing and the merge as just one detail that we do along the way. It's got it wrong. I don't like this. Okay? I prefer this diagram. It's about integration. It's not about our build cycle. It's about how frequently we integrate, how small we integrate. That's what we want to do. And you know what? Why do we need those continuous builds? Well, if we go back to the old way of doing things, where we had a 12-month-long project and integration happened at month 11, and by the way, it never went well. In that period, it was, if we had a 2-week-long test cycle, well, there's no way we're going to be able to integrate every 10 minutes if we've got a 2-week-long test cycle. Of course not. We needed to optimize that test cycle so that we could do it quickly and fast. It's only by getting through all those tests that we know that we're safe to integrate the stuff, which is why we need fast, automated builds. But those builds only exist to enable, effectively, trunk-based development. So, continuous builds exists only to enable continuous integration. And when I'm saying you need continuous integration, you need it in the true sense. You need continuous integration, not just continuous builds. And the benefits are that you have fewer big mergers and deployments, which are horribly painful, and they're like the hardest thing about programming. They cause so many issues, and so many bugs are only picked up when we integrate stuff. Like it's all very well and good telling me that your branch works, but does your branch work when you've integrated it against mainline? If you haven't integrated it against main, then I don't care about the results of your test, because you've not tested it in combination with the work that's on mainline. You get a more resilient set of changes, because significantly more frequent and smaller changes are much easier to understand. They're much easier to fix. The impact of the likely impact of failure is significantly smaller because you've only changed a small amount of stuff. And the mean time to recovery is going to be a lot quicker because it's much easier to figure out if it went wrong, why it went wrong. You're only deploying one small thing. So it's much easier if it goes wrong to figure out why it went wrong, rather than trying to deploy a year's worth of code at once to this application, that database, and this service, and whatever else. Like, you're just making one very small change, and if it goes wrong, well, that's why it went wrong. It's because of this change. Back that one small change out is typically a lot easier than backing an enormous release out. simpler project management as well. So much project management is to do with managing this piece of work and this piece of work and this piece of work, and when we're going to release that and when we're going to release this, and making sure that these two teams don't go too far off from each other and that they're integrating and having regular meetings to talk about the blah, 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 blah. All of that pain is as a result of having way too much work in progress. Well, if there's only ever the last couple of hours worth of work on your branch, that's not a huge amount of work in progress. You can just merge that as you go. So the project management stuff gets an awful lot simpler as well. You end up with much more realistic planning, because when we're talking about, for example, switching plans, estimates of how far we're going to get, how long it's going to take us to get somewhere, well, we've already got like the lion's share of the stuff is already merged and deployed to production anyway. So we know very specifically how much stuff we've got left to do. And we're confident that the stuff that we've done so far is okay. So it makes it much easier to plan. And also, it gives us improved agility. If we get 3/4 of the way through some feature and then, I don't know, there's a global recession and suddenly it changes everything about the way that we live and work from home, and suddenly we need to support home working, and that has had a radical implication on so many different pieces of software. If some curveball like that comes along and just fundamentally changes the way that the economy is working, and we need to modify our plans to keep up with the market or to embrace some new opportunity, then having worked like this means that we've already banked all the work that we've done so far, and we're free to go and do something else if something else becomes more important at short notice. So that gives us that increased agility. It comes with certain challenges, obviously, balancing long-term vision versus the rapid iterations and potential changing of plan. That's always a challenge, but that's a challenge that we've had since Agile came along. Reviews and oversight become harder. In a world where you had a 12-month release cadence, then perhaps it wasn't so much of a problem if you took a week to review the code. But in a world where we're releasing potentially multiple times a day, then a 2-week wait for the next change approval board meeting just isn't going to cut it. So I appreciate that we need an appropriate level of oversight on some changes, and code reviews are great, and we need a bunch of automated tests and stuff, but we need to rethink the way that we prioritize those code reviews and the way that we handle them, so that we handle them in a timely fashion, and we only waste time on them where it's required. Let me rephrase that. We only invest the time in the review where that investment is likely to yield a result. And we also need to solve the problem of dealing with regular updates. So how do we live in a world where all the software around us, all of our dependencies are changing all the time? And that brings us on to loosely coupled systems. So in the diagrams here, you can see in the one on the left, we've got a monolithic system where we've got one central database, which is on fire, and we've got 3 applications on top of it. And because the central database is on fire, all 3 of the applications have gone down. On the other side, we've got a more loosely coupled system. Our applications each handle their own data. So when we have a fire in one of the databases, the other 2 can keep running. This is us taking the single responsibility principle and the separation of concerns and applying it to our architecture. And ideally, each one of these, I'm nervous about using the word microservices, because then I'm going to get people in the comments, and I'm not necessarily advocating for kind of full-on microservices. But in general, if we can separate our database out a little bit more, that's probably a good thing. One of the problems that we have at the moment is that database has been ultra normalized, and everything is a foreign key of everything else, which means that it's all tangled up and is very difficult to separate out. So as a database administrator or a database architect, for example, right now, if you're living in the diagram on the left, the idea of how we move to the diagram on the right might sound really, really hard. So what can we do about that? Well, the first thing we can do is read about domain-driven development. And this is about basically understanding what bits of the puzzle the various different systems need to look after. And once we've done that, we can start looking at things called bounded context. Now, the easiest way to talk about bounded context is to open up Martin Fowler's bounded context blog post and look at this diagram here. So in this example, we have a sales system and a support system, and the sales system cares about stuff like opportunities and pipelines and salespeople, and the support system cares about things like tickets and defects. Both systems care about customers and products, and that's great. But they don't have to look at the same customer table and the same product table. All they need to do is recognize that they're both calling these things, and then they can agree on some standard schema or interface to use to define what a customer or a product look like. Then they can each look after their own customers and products, and they can communicate not directly database to database, because that's where we end up with nasty, horrible dependency issues that are just hard to deal with. We can go kind of through the app and through the API tier at the top, or some other communication tier up there. And that's how we can do our communication. And then all I need to do, as somebody working on the sales system, all I need to do is test that the API calls work on the support system, and that's all I need to care about. I know what my API calls are, and I can mock and fake those out in all of my testing. I don't need the support system. As long as the support system has automated tests to verify that it's got API calls that return the correct results. That means I don't need to host the sales and support stuff in the same place. The databases don't need to talk to each other at all. They can be on completely different hardware and completely different clouds, whatever. I don't care. When one is affected, hopefully the other one is not affected, because they're not sat in the same place. They're in different places entirely. It means that, for example, if the sales system goes down, hopefully the support team can still support your customers. There might be a little bit of lost functionality because they might not be able to look up kind of all the sales data. But for their core operations of helping their customers with their support tickets, hopefully they can still run even though the sales system is having problems. And this gets to the heart of why loose coupling is more resilient. It gives us fire breaks around the various different subsystems. And as well as that, first of all, simple stuff like provisioning dev environments gets a lot simpler. When a salesperson needs to provision a dev environment, they don't need the support stuff. They can fake that stuff out and mock that stuff out. When they're developing, they don't need to worry about how the sales system has been implemented. All they care about is the API calls. That's all they need to worry about. They need to care about those API calls. They need to care that they're online. But apart from that, it doesn't matter. They can concern themselves purely, like the scope of what they need to know to be able to do a good job of developing is significantly smaller, which means it's a lot easier. Testing becomes a lot simpler because all they need to do is test their subsystem. They don't need to worry about the whole monolithic relationships and dependencies. I don't care about any of that. I just need to test my thing. Deployment becomes a lot easier. I don't care when the sales system has been updated because it doesn't affect me. As long as those APIs are available, and there'll be some sort of, I'll talk about service level objectives in a minute, as long as they meet the uptime stats that they've promised, that's their concern. I don't care about that. I can deploy when I like. Continuous integration gets an awful lot easier. Look at these two diagrams. Imagine I've got 30 developers. On the left-hand one, I've got 30 developers all working on different things at the same time, and they all impact the same database. That's a headache. On the right-hand diagram, my 30 developers are split across 3 different systems. Even if they're split evenly, that's 10 on each system. Managing the concurrent development of 10 different developers is a lot easier than managing the concurrent development of 30 developers. Loose coupling is more resilient. As I said, we have better fire breaks. We need to defensively code against other systems being down. We need to run in some sort of deprecated mode. Once we architect our stuff like this, our human problems become a lot easier as well. So you've probably heard of Conway's Law. It says that your software architecture is destined to mirror the lines of communication at your organization. The old adage goes that if you have 4 development teams working on a compiler, you'll get a 4-pass compiler. With loose coupling, we are able to disconnect the various teams from each other, which gives us huge advantages from a bureaucratic point of view as well. It means the decision making can live within the team. We don't need to do everything by committee. Teams can focus on their goals. When we talk about their goals, I can talk about service level objectives. So DevOps often talks about the conflicting objectives between dev and ops, where dev want to move fast and ops want to move safely. Well, if dev and ops live in different functions and have got different and report to different members of the board, different members, different vice principals, like right at the top, then they're never going to agree on things, and we're setting them up for war. However, if the people that own both the speed and stability objectives lives within the same team, and they consider themselves part of the same team, and they jointly own those goals, suddenly these conversations are set up for debate and discussion, intelligent, thoughtful debate and discussion about how we achieve both of these things at the same time, rather than how we beat each other into submission. Now, these SLOs, let's say, for example, and to give a hugely oversimplistic one, let's say 3 nines. So what that means is I want 99.9% uptime, which equates to about 42 minutes a month. 42 minutes a month of downtime. I have to be up the whole of the rest of the month. As a team, if I've habitually gone way underneath that and I'm way more stable than that, well, maybe now's the time to take a couple more risks and try and move faster. Equally, if I'm always struggling to hit that SLO, well, maybe now is the time to slow down a bit and try and focus on making my thing a little bit more stable. These things are all arbitrary, but they give us a clear thing to aim towards, and they help focus the discussion based on what the business needs. If the business needs this system to be ultra reliable, then you get a tight SLO. If the business needs this system to make rapid progress, and maybe it'll forgive a little bit of a few errors here or there, as long as you're making progress to whatever business innovation goal you've got going on. These things can really help speed that conversation along. And also, if you have dependencies on other systems, you know what their SLO is. And so you're not going to design your product to expect anything beyond what their SLO says. If the sales system knows that the support system is only expected to have 99.9% uptime, it's not going to expect 5 nines uptime. It's going to be built with the expectation that for 42 minutes a month, the sales system the other system is going to be offline. And that's good. That means that we're building defensibility into our system. We're building resilience into our system, and that's great. The bounded contexts, as I said, give us bounded autonomy, which means that our individual teams are now, they don't need to wait. Like, remember in the downtime hell scenario where you needed to negotiate with every single other person in the business to be able to get your downtime window so you can deploy stuff? Well, no. You can manage it within your own team. Your team knows what your SLO is, you know who your customers are, and everybody else knows that you're only online 99.9% of the time, which means that gives you that little bit of freedom to play with and to innovate with and do the best work you can. The last thing I want to mention here, which is a bit different, is that, and this was addressed by Richard Cook earlier, is that failure is an innate part of humanity. We're humans. We're not perfect. We make mistakes. And it's only through making those mistakes, and it's only through experiencing failure and working through that failure, that we get better, that we improve. Somebody who's been through a few battle stories is likely to make a safer engineer than somebody that hasn't. And I really like how well this is articulated by the old anecdote about Tom Watson at IBM, which is told all over the place, but I'm going to tell it again now because it's a good one. So IBM had just managed to survive through the recession the depression in the 1920s. Having said that, like, business was tight. They didn't have a lot of free rein, but they'd survived, and that was good. A sales exec was working on a deal, and he lost it. It was a key deal. It was really big for IBM. It was a massive kick in the face that they didn't get it. And so he went into Tom Watson, the CEO's office, and he handed in his resignation. And Tom Watson said to him, "Can you tell me what happened there?" And the salesperson said, "Well, I made this mistake. I didn't get that right. And as a consequence, this happened. And you know what? If I was doing it again, I'd do it this way and that way. But it's water under the bridge. I understand that you're not going to want me anymore, so..." And then he went to walk out the door. At which point, Tom Watson stood in front of the door and said, "Why would I accept your resignation? I've just spent however many $1 million training you." He doesn't want to put that investment to waste. And it's that story about, yes, we don't intend for these training opportunities to come along, or sooner that they don't come along. But when they do come along, that's a scar of battle. And it'll earn you some respect, which is a line I stole from one of my favourite songs that I discovered recently, which I reference in the blog post that goes along with this bit, the human side of loose coupling. I'm not going to play the whole thing to you now because because you can watch it on your own time. It's only a couple of minutes long. I'd like to finish. I'd like to finish with a recommendation that you go and watch this song, because for me it screams everything about the sort of organization I would want to work for. Not just because I think it's much more humane, but also because I think I'd grow a lot more there as well, and I think that we'll deliver better systems together. And that's the sort of organization I want to work for, one that values its people and treats them with humanity and respect, and accepts that sometimes humans make mistakes, and uses those as learning opportunities. It's called the Hug Up song. So yeah, go check it out. So to recap, we talked about Dante's database hell, and I put it to you that more resilient systems, where we embrace continuous integration in its true sense, and we embrace loose coupling for various technical and human reasons. If we can work to that sort of future, a whole bunch of the problems that we discovered, that we talked about with the database hell, go away. A bunch of the vicious cycles disappear. And in fact, what we've done here is we've created a bunch of self-enforcing good things that might help us to climb out of this hell one day. And in the next talk, in beginning of December, Derek and I are going to talk about various technical practices that can help us along the way. I'm not promising to solve all of your problems. If I could solve them all in an hour, then I'd be retired by now. But there are a few technical practices that I think are really going to help you with this journey. There are a few things that I've kind of implied there, such as zero downtime releases, which you might be wondering about practically how do we put all that together. So that's sort of stuff we're going to talk about next week. I'm really looking forward to it, and I hope I'll see you there. Time for some questions.
Okay, Alex. I love how you said Derek and I. I'm literally just your host. There's actually not that many questions. So, what I'm going to do is I'm going to start with where do you start with all of this? Obviously, with the database side of things all changing and adopting database DevOps, where do you think is a good place to start on that, just to help people in today's webinar when they go to adopt these changes?
Yeah, it's a very good question. There are all sorts of there's so much. The first thing I would do is try and figure out a portion of your system that is reasonably self-contained and where you can be reasonably autonomous. Because having, I guess, a little area where you have a little bit more control means that you can start having a real effect with a smaller group of people without having to get buy-in from everybody else. And once you've got that, implementing, and from a technical perspective, I care about things like source control and self-service environment provisioning. Once we can do that, it means that we have significantly more resilient dev systems. We're more able to practice continuous integration. We're no longer coupled to everybody else in the dev domain. And if we can start demonstrating some success there, then hopefully we can start conversations with people and start demonstrating a little bit of success. The other thing I'd say is measure things. There's a fantastic quote, I think it's from Accelerate, where they say, I can't remember exactly what the quote is, it's by Nicole Forsgren. It says something along the lines of, the key to all this is figuring out what to measure and measuring the right things, with a focus on capabilities over maturity. Basically what I'm saying is, figure out what your goals are, measure them, and then try to demonstrate with data that you are achieving those goals. So for example, if we're talking about resilience, I mentioned a few things there. Mean time to restore.
Recovery.
How quickly can you restore systems?
Yeah, that's a really great point. David is asking, often his database in production and test and dev, they look very different. And what happens is sometimes they get to production and they do a deployment and there's a big bang moment. What's your recommended approach for that? Do you sync the databases? How would you go about doing all that?
Yeah, it's a very, very common problem that dev and test and production look radically different from each other. This problem is not going to be fixed until you are shipping more frequently in smaller batches. This is the whole point of the continuous integration part that I was talking about. So the first thing is to try to shift towards smaller, more frequent deployments. There's a whole chicken and egg thing here, though, because often the reason they are infrequent and big is because they're risky and there's not a huge amount of confidence or trust that we're going to avoid breaking things. So it's a whole chicken and egg thing. But if we try and start focusing on doing smaller things and working in smaller steps and cleaning up all the looking at all the things that are different on dev and test as well and saying, look, is this unfinished work? Is it still in development? Can we kind of bin it off or kind of put it off to one side? If we're not actively working on it, can we sync this test environment with what production looks like? And one other thing is moving towards more of a self-service dev environment provisioning process, because if it is possible and practical for a developer or a tester or an ops or whoever to spin up an environment that is based on production, a standard image, if you like, if we can do that quickly and easily without having to jump through 15 levels of approval, then it means that all of a sudden just there's a culture of using these standard dev images that hopefully all look the same. And at that point, also we get to the point where our dev infrastructure is truly disposable. When I've finished doing a piece of work, I kill it and I build a new one. When I break something, I kill it and I build a new one. And then when I get to that point, there is no delta beyond the current piece of work that I'm working on my dev image. And when I break stuff, I'm not hurting anybody else. And a lot of these problems tend to go away at that point, or they don't go away, but they, to a certain extent, you're trading one set of problems for a different set of problems, but you're in a much better place.
Excellent. Well, unfortunately, that is the end of the questions. James is asking, actually, could you share those links that you had, the Hug Up song for everybody to click on and dance away to?
Yes, I can do that. I actually have. I'd actually typed those out in the notes on slides and things. I've got that on another monitor. Just bear with me. I'm going to copy and paste that in. Okay. If I paste that to everybody, if you look in the chat window now, awesome. That's just pasted directly from my notes. So apologies if there are failure, if there are typos or anything in there. So that's hopefully all the links you need, and I guess we'll add them to the YouTube.
Yes,
or YouTube comments or something later. If there's anything in there that I've missed, then shout at me, and I'll try and find whatever it is you're missing.
Awesome. Thank you so much, Alex. That was absolutely fantastic. So at this point, we are at the end of today's webinar. We've got some resources for you. If you have any problems with Octopus, reach out to our support team at support@octopus.com. If you've got any questions about licensing, you can get in touch with sales@octopus.com. And we also have a customer solutions team. This is more about how you do X with Octopus. You can email advice@octopus.com. We do stream all of our webinars onto YouTube, and we've got a whole bunch of other stuff there. Please do check out youtube.com/Octopus Deploy. If you can, stick I always feel a bit awkward saying this, but do hit that subscribe button. We've got some really great stuff coming up, and we're hiring. Check out octopus.com/company/careers. We're hiring in the UK, the US, Australia, and New Zealand. And Alex has got an 8-part blog series that I would definitely recommend checking out. If you go into Safe Schema Updates 1 Delivery Hell, or just octopus.com/blog, and you'll be able to see that. Alex, thank you so much for today's webinar. I'm not quite sure I can stick my name on this one. That was absolutely fantastic.
It's been a pleasure. Thanks for having me.
Awesome. And thank you all for coming along and attending today. A recording will be emailed to you probably on Friday. We do have some upcoming webinars. Alex is back again, talking about building better systems. This one's going to be a good one. And then Trish Koo and our new member of the team, Sarah Lean, is back on the 15th and 16th, talking about remote engineering management at Octopus Deploy. That'll be a great one for the budding development managers out there. Okay, so thank you so much. Enjoy the rest of your day, and I'll see you next time.
See you, folks.